Hey everyone, welcome to our next lesson on oxidation and reduction reactions. These are pretty neat reactions. We're going to take a look at three different types specifically, and then talk about and learn about what it means to be oxidized, reduced, and exactly what a spectator ion is. And then we'll take a look at how we can determine what a missing species might be in a redox reaction by comparing or using our law of conservation of matter. So to start off, why do reactions happen in the first place? Why not just not react? Why not just stay as reactants and not have any type of change happen? Well, reactions have motivation to them, or a driving force. And this driving force is what's going to allow the reaction to proceed from reactants to products. If we think about this driving force in nature, nature likes to conserve energy. So a change that happens in nature that requires less energy is more likely to happen than one that requires a lot of energy. Just like a sled at the top of a hill. Its motivation, its driving force to come down the hill would be gravity. Gravity is going to naturally take that sled from the top of the hill to the bottom of the hill, converting potential energy into kinetic energy. So redox reactions, their motivation or driving force is the loss of electrons or the gain of electrons. Now, these terms are known as oxidation and reduction, loss of electrons being oxidation and the gain of electrons being reduction. Want to make sure that we know those two terms. Now, in these types of reactions, one species will gain electrons and another one is going to lose them. They're basically going to transfer electrons from one species to the other. So these reactions are prompted by an exchange of electrons between two elements, which changes the oxidation number of the species that are involved, or of the two elements, if they happen to be elements that are involved. Now, the more electronegative element, which is usually going to be our nonmetal atoms, and since they're more electronegative, will gain an electron, which will result in a decrease in oxidation number, which means it's going to get more negative. Sometimes I think this is a little confusing, calling increasing and decreasing oxidation numbers, but decreasing meaning we're getting more negative, we're going towards that negative end on the number line. So we gain electrons, each electron being having a value of -1. That is going to be called reduction. In a sense, we are reducing our oxidation number. Whichever element is less electronegative or has less of a desire to obtain an electron, it is likely to give up that electron and lose it to the species that is being reduced, which will cause an increase in the oxidation number for this species. So if we lose electrons, that is called oxidation. So in a redox reaction, there's always going to be something undergoing reduction and something undergoing oxidation, because in order to receive an electron, we also have to have something that will give up an electron. The three types that we will talk about, we'll learn about: synthesis reactions, basically taking elements to form a compound. Decomposition would be breaking a compound down into component elements. And we'll take a look at some single replacement reactions, which involve an element and a compound exchanging positions, essentially. And I'll show you a couple examples of that, of those types of reactions in class. Each of these three does involve some species being oxidized and one being reduced. We have to have one with the other. Now, in order to do these types of problems, we got to be able to determine the charge that each of our species has, so we can kind of keep track. Does the oxidation number change from beginning to end, or does it remain the same? So we have to look at the charges for every species that's involved. If the element is by itself, there is no charge. Its oxidation number would be 0. We can look up these values on table E if we're dealing with polyatomic ions, or on the periodic table if we're dealing with just regular element ions. If the element has more than one charge listed under its list of oxidation numbers, we're going to use the other ion's charge, or the negative ion's charge, to determine the charge of the positive ion. Let's see an example. Take a second to try and name this. I want to get in the habit of trying to practice that every time you see a formula. This is aluminum sulfate, Al2SO4 3. Aluminum is listed on the periodic table having an oxidation number of +3. SO4 is on table E. It's a polyatomic ion and has a charge of -2. So to kind of put this together, each aluminum is a +3, and we do have 2 of those. And we have 3 SO4s, 3 sulfate ions, and each one of those is -2. Take a second and try and name this. If you said iron phosphate, you are correct. Iron has 2 charges listed on the periodic table, +2 and +3. So we can have iron 2 and iron 3. Phosphate is listed on the table as being a -3 on table E. So these could be put together in a 1-to-1 ratio, but our formula is telling us that it's not a 1-to-1 ratio. So in order to make these add up to 0, iron has to have a +2, because +2 times 3 irons gives us a total of +6. And we have 2 phosphates, each at a -3, which gives us a total of -6. If we used iron 2, that would give us a total charge of +4, which would not balance the -6. Again, we want those oxidation numbers to add up to 0. Alright, synthesis reactions. The general formula that you'll see for these are 2 elements that are going to combine to form a compound, such as saying H2 plus O2 yields us H2O, and then to balance that, we will go 2H2O and 2H2. This is the easiest way to make a compound in an industry. That is often what it is used for. It takes the general form A plus B yields AB, compound AB. This can kind of take any order, but we'll refer to species A as the one being oxidized, and B being reduced, since it is going to gain an electron and become negatively charged. The positive indicator here means that we lost electrons. This one means we gained electrons. An example here, we have magnesium plus oxygen yields magnesium oxide. Elements by themselves get their oxidation charges of 0, and once they're combined, we can determine the charge. Magnesium is always +2, oxygen is always -2. It's a nice easy 1-to-1 ratio. So magnesium will lose 2 electrons, increase its charge to +2. Since it's losing electrons, it will be oxidized. Oxygen is going to gain those 2 electrons and decrease its charge down to -2, so it is being reduced. We are comparing the numbers, magnesium before to after the change, and oxygen before to after the change. We're looking for how much they're changing by and which ones are changing. Next type are called decomposition reactions. These rarely occur on their own, since compounds exist because it takes less energy to exist as a compound. That's why things bond together. They can move to a lower energy state and exist at lower energy. In order to break that down, it's going to require a fair amount of energy, which is why these reactions don't necessarily happen on their own. This type of reaction we use to get highly reactive elements, such as our halogens, out of compounds and into a pure form. This process, which we call electrolytic decomposition, uses a strong electric current to break the compound apart into its component elements. So starting with compound AB, this is our general form here, we would separate it into elements A and B. A and B would both start with a charge since they're bonded together in a compound, but one separated would return to an oxidation state of 0. Since B goes from a negative value to a value of 0, it is losing electrons and therefore gets oxidized. A is going from a +1 to a 0. That's getting more negative, which means A has to be reduced by gaining an electron. An example of decomposition, hydrogen peroxide. This is why hydrogen peroxide is put into a brown bottle, because it reacts with ultraviolet light. And will proceed in this manner. So if you expose hydrogen peroxide or have old hydrogen peroxide around, it will break down over time into water and oxygen. And if you don't release the oxygen gas out of that bottle, it can explode, especially if the hydrogen peroxide decomposes rather quickly. So we identify within the compound of H2O2 what our oxidation numbers are. This is one of the rare cases where oxygen is a -1. We look and see how those charges change for oxygen, change for hydrogen. We also have ones that go to here. So we have two different oxygens gaining and losing electrons. O-1 gains electrons, charge decreases, so it's being reduced. It's also going to lose electrons, increase in charge, so it is also being oxidized. This is a pretty rare example. Single replacement reactions, I love these types of reactions. These can occur between metals in a compound or non-metals in a compound. Whichever one they're going to be, they're always going to have one element and one compound on both sides. And basically we're going to play a little game of switch your seat. So the metal is going to replace the positive ion in the compound. It's going to come in here and replace B, and B is going to get kicked off and removed out of the compound. A takes its place. These types of reactions are used to produce electricity in a battery. Also used to get less reactive elements out of compounds. We apply our oxidation numbers here. A by itself gets a 0 in the compound. Again, this is a general form. B or C, one's going to be positive, one will be negative. And then we can see how they switch here. A comes in and kicks out B, and A, since it's taking B's place, is also going to be a positive ion. B gets kicked off and decreases its charge from a +1 to 0. C remains the same. So since A lost an electron, it is oxidized, it increased its charge. B positive gains an electron. Get rid of that there. Decreases in charge, so it's being reduced. The C minus doesn't change in charge, so it's what we call a spectator ion. It is essentially spectating or watching the reaction happen, but it is not directly involved in what's going on. Here's an example with a metal in a compound. In these types of examples, the metals come in here and kick each other out. And we have kind of a swap that occurs here. We still want to always compare our oxidation numbers from before to after. And nitrate. We'll do it for each of our species here. The zinc 0 loses 2 electrons as it bonds with 2 nitrates. Increases in charge, so therefore it has to be oxidized. Copper +2. It's going to gain those 2 electrons that zinc lost. decrease its charge, so it's being reduced. And that nitrate is going to be the spectator ion. It doesn't change its charge. The polyatomic ions are always going to be your spectator ions since they don't change charge. Now an example with a nonmetal in a compound. Here we have fluorine and zinc chloride. Same idea will happen. Fluorine and chlorine are going to swap places, the two nonmetals here. Chlorine is going to go from a -1 to a 0, so it's increasing in charge and therefore has to be oxidized. Fluorine goes from a 0 to a -1, therefore gains an electron, decreases its oxidation number, and therefore is reduced. The zinc 2+ remains 2+ as a reactant end product, doesn't undergo any change in charge, so therefore it is the spectator ion. One of the things that you have to be able to do is identify types of reactions by looking at them. So this first example here starts with an element and a compound, zinc and potassium nitrate. Gives us zinc nitrate and potassium. Since we start with an element and a compound, it must be single replacement. Next one, we have iron and chlorine yields iron chloride. We start with just elements and end with a compound, so this must be a synthesis reaction. This last one here, sodium nitrite, yields sodium, nitrogen, and oxygen. This is taking a rather large compound and breaking it down into 3 different elements. But we are starting with a compound, ending with elements, so it must be a decomposition reaction. So at this point, you should be able to name and identify 3 types of redox reactions: synthesis, decomposition, and single replacement. So I want to be able to identify reduced, oxidized, and spectator ions. We can tell that by looking to see which species lost electrons. Its oxidation number becomes more positive and therefore would be oxidized. Species that is decreasing its oxidation number must be gaining electrons, and therefore its oxidation number becomes more negative. The spectator ion will neither gain nor lose electrons, and therefore its charge is going to remain the same. Here's an example. What's oxidized, what's reduced, what is the spectator? Feel free to pause the video and try this before the answer is revealed. Again, we want to start with our species here, a 0 to a +1 and a 0 to a -2. Silver, Ag0, is going to be oxidized. It goes from a 0 to a +1. It's getting more positive, therefore it's got to be losing electrons. Oxygen 0, as a reactant, is going to gain 2 electrons and therefore be reduced. There are no spectator ions in this particular reaction. What type of reaction is this? Well, it's got to be synthesis. We have 2 elements forming 1 compound. Here's another example. We compare here K0 to a +1. We're getting more positive, therefore we have to lose electrons in order to get more positive. So the K0 is a species that is being oxidized. The K +1, if we think of this in the other direction, would actually be reduced, but we haven't really gotten into reversible reactions yet. And we're going to read these left to right, indicated by the arrow. Al3+ goes to an Al0. We're getting more negative, therefore we have to gain electrons and be reduced. The spectator ion, sulfate, doesn't change charge from reactant to product, and therefore is our spectator ion. Starting off with iron oxide yields iron and oxygen. We compare our oxidation numbers here, -2 to 0, +2 to 0. Oxygen is going to be oxidized as it gets more positive, charge values increasing up to 0, and the iron is going to gain electrons. This is not favorable. This type of reaction, again, it's a decomposition reaction, starting with a compound and going down to component elements. This would not be favorable. This would not occur on its own. It's going to require some outside source of energy. But iron goes from +2 to a 0 and therefore has to gain 2 electrons. In this particular example, there are no spectator ions. So you should be able to identify species that are being oxidized, reduced, and identify any spectator ions in a redox reaction. The last thing we'll do today is work on finding the missing species in a reaction. When we're looking at different reactions, if the missing species is an element, all we have to do is write its symbol. Just remember, if they are diatomic, remember Brinkelhoff, we have to write it as being diatomic. Otherwise, the reaction will not balance. If the missing species is a compound, we always write the positive ion first and the negative ion second. And we'll want to write this formula in such a way that we have the same number of atoms of each element on both sides of the balanced reaction. So it gives us a way to kind of verify that we wrote that right. So in this example, to the left of the arrow we have silver and oxygen. Therefore on the right we have to have silver and oxygen. We need a total of 4 silver on the right and a total of 2 oxygen on the right. This will help us kind of figure out what our formula might be. So we know what we need on both sides. Silver is the positive ion. We're going to write that first. And we get 2 Ag2. Distributing the 2 here gives us 4. And the 2 here gives us 2, which match the 2 and match the 4. So that balances. Another example. We can look at everything we have on the left side. On the right, we only have aluminum. So we're left with K and SO4. Now we just got to make sure that we write that in the appropriate way and accounting for the coefficient here. So the missing species are 6 potassiums and 3 sulfates. We have the 3 here, so that should kind of help indicate what our formula might be. We're going to want 3 sulfates, and given that 3 there, we're going to multiply that by 2 potassiums to get our total of 6. So we end up with our formulas K2SO4, the 3 being distributed here, which gives us 3 to match the 3, and 2 potassiums, excuse me, that would be 6 potassiums to match the 6 here, 2 aluminums, so we balance. Try another one. This is a decomposition reaction starting with a compound, ending up with, well, at this point, 1 element, but we're missing oxygen. It is diatomic, so we have to write it diatomically, part of Brinkelhoff, and that will allow us to balance this reaction appropriately. We're now left with 2 irons, 2 oxygen, 2 irons, 2 oxygens. Feel free to pause the video and try this on your own. So we can see that we're missing a couple things. We have 2 aluminums, which match here. We'll account for that 3, but we're missing silver and carbonate. You can see we got a 3 here, but we got a 6 there. So we're missing 6 silvers and 3 carbonates. Since we have the 3 coefficient, the compound contains 2 Ags, because 3 times 2 is 6, and 1 carbonate, because 3 times 1 is 3 total carbonates. So we get Al2CO3, 3. Or excuse me, Ag2CO3. We're looking at the reactant there, not the product. You should be able to determine the missing species in a redox reaction. Make sure you write down any questions that you have, and feel free to raise them during class when we review this tomorrow. Hope everyone has a great day.